Welcome to lesson 56, a library of functions. Got a new word today, functions. And library means I'm going to show you about 4 or 5 typical functions and say, hey, these are cool, and we'll keep playing with them for a while. But before we can get to that, first we should talk about what the heck is a function. So I'm going to spend a little time up front just talking about what is a function. So let's just kind of go by an example. I'm going to make up an example of something that happens to be a function. So first of all, think of a formula. Okay, I'm thinking of a formula. I just thought of a formula. Y equals x squared. Nice formula. It's a formula where when you plug something in, well, then you get something out. Yeah, that's what formulas do, right? I plug in values for x and I get out values for y. Okay, so far so good. If you can rely on each input to give you only one output, and it's the same output every time, then we call it a function. So I made up this nice little formula, y equals x squared. Now, to prove that it's a function, I have to show that when I make up anything for x, and I do mean any number for x, if I plug in 0, what's going to happen? I'm going to get each input, I can rely on it to give me one output, always the same output every time. I'm saying kind of two things there. The output, when I plug in x equals 0, is y equals 0. That's the only output I get. And it's going to be the same if I do it again tomorrow, right? If I plug in like a 1 and I square it, I get y equals 1. I only get 1. That's part of what we need. Gives you only one output. And if I do it again tomorrow, I get the same value. It's the same output every time. Okay, so these are the key features for that formula there to count as a function or to be describing a function. We need that property. If I plug in -3, anything I make up, if I plug in -3 here and square it, I get a positive 9. That's the only answer, and it's always that answer. Okay, so most formulas we play with in real life are functions. Not all of them, but most of them are going to be functions, and we're going to actually limit ourselves pretty much to functions for the rest of the course. But that's the idea. That's what you need. Now, if you were to, I almost wish I hadn't deleted it, but I did. If you had graphed that thing, this is what we're saying here. If you were to plot the inputs on the x-axis and the outputs on the y-axis, the resulting graph will always pass a vertical line test. So this was the formula I was playing with. Turns out if you graph that stuff, you're going to get a parabola. When x is 0, y is 0. When x is 1, y is 1. When x is 2, y is 4. When x is -1, y is 1. When x is -2, y, and so on. It maps out a really nice parabola shape. And the thing to note about the parabola shape is it passes what's called a vertical line test. Any vertical line that you care to make anywhere will never cross the graph more than once. It'll intersect the graph at one point, if at all. It doesn't have to intersect the graph. But if it does, it only intersects it at one point, never at 2 points, never at 3 points. So what that means is things like parabolas are functions. Things like circles are not functions, because if you draw a vertical line here, oh, I cut in the graph 2 places. Not a function. Okay. By the way, the reason it's not is because if you were to try to, here's what the equation of a circle looks like, something like this. So notice that if you try to get y by itself in order to plug stuff in, you have to do this stuff, taking the square root of both sides, which means plus or minus. And that means that when you plug in a number for x, you figure out what this is, you take the square root, and then, oh, plus or minus, yeah, because you have one up here and one down here, plus or minus. Okay, you don't just get one output. You're supposed to get one and only one output. Okay, that's why the circles are not functions. Anyway, let's get rid of all this stuff. We kind of don't need this anymore. So we're not going to have to worry about this too much. I just want you to know what a function is. It passes a vertical line test. It has this nice property. When you plug something in, you only get one answer, and it's always the same answer. Today, tomorrow, and the next day. It's always the same answer. Cool. Here's a little terminology. I suppose I should put that graph back again. So here's a little terminology. Let's say that was your graph. Okay. We refer to x as the independent variable. So like in your XY table, we have a whole bunch of values, right? When you plug in -1, you get 1 and so on. Oops. You know, we've got all these XY values, right? This we sometimes call the independent variable. What's so independent about it? Well, when you're making your XY table, you're saying, yeah, let me make up something for X. It's the variable that you kind of make up. Let me make up something for X and plug that in. It's the thing that you're plugging in. I'm plugging in the X here. That's what I'm doing. That's called the independent variable. What you get out, we call Y sometimes. And that would be the dependent variable because it depends on what you plugged in. Okay, cool. So that's all that is. And then one more final note here. The set of all possible inputs is called the domain. The set of all possible outputs is called the range. Hey, nice typo I just found. The range. So anyway, domain and range are words you're going to hear a lot, so you want to know what those mean too. So domain, let me see here. Try to erase just the green parts if I can. Cool. The domain would be, try to imagine taking every single possible number that goes in the X column and putting them into a set. The set of all possible X values from here. That's what we mean by the domain. The set of all possible inputs, X. All of them that are possible. That's called the domain. What's the domain for this function? For this function, notice we can plug in anything we want. The graph goes forever to the right, it goes forever to the left. So actually for this one, the domain is all real numbers. All real numbers. In interval notation, from -infinity all the way to +infinity, go forever to the left, go forever to the right, never stop ever, every single number in the world, every real number in the world. And as far as the range, you kind of do something a little bit different there, because you don't look at the X, you look at the Y. It's the set of all outputs, which is what it's saying here. The range is the set of all outputs. So if you took not just the 1, 0, and 1, but every possible output in the world, and you put them in a set, that would be called the range. You can kind of tell by looking at the graph what's the range for this thing. Well, notice we never get any graph down here at the negative values of Y. So the range here would be all, Y can be anything greater than or equal to 0. Right? We can get Y equals 0 here. But then you always get bigger values for Y, no matter which branch you go up. You always get values for Y are 0 or anything bigger. If you want to do the interval notation, 0 with a square bracket up to infinity like this. Okay, so those are the main vocabulary things that go with this. Now let me get this stuff out of here because it's crowding me, man. It's crowding me. Get this stuff out of here. Here's what we're gonna need to get used to today in particular. Is the notation for a function. So if you have a function, let's just call a function a formula that behaves well. You plug in something for X, you only get one answer for Y. Okay, it behaves well. The graph passes a vertical line test. You can talk about domain, range, independent, dependent variables if you want. But here's the thing that we really have to do. We have to adopt a function notation. When you have a function, instead of just saying y equals x squared like I did before, we're going to adopt this notation. Y is a function of x. It's a function of x because it worked. When you plug in a value of x, you only get one value of y, blah, 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 blah. It worked. It is a function. We say that it's a function of x. In fact, let me write this down. Y is a function of x. That's one way to read this. Y is a function of x. Now here's the thing. A lot of times we just dispense with the y altogether. Instead of saying y equals x squared, we'll write it this way. We'll just kind of rub the y out and just write the f of x in its place. This is what we've really got to get used to. Instead of saying y equals x squared, which is what we've done since we were kids, right? Y equals x squared, that makes sense. You plug in x, you get out y. Yay, yay, complete yay. Well, now we're going to adopt this notation where instead of using a y, we're going to use an f of x in its place. So in some sense, f of x is a glorified version of what we used to say was y. It is the output. So the output is f of x. Oops, let's get a real pencil here. What do you say? What do you say? So x is our input or independent variable. F of x, look at that as one thing. F of x is our output or dependent variable. Sometimes we'll use a y. You'll see me use a y all the time because it's just easier to think with a y, right? Y equals x squared, but f of x, that's what you call the output. So for this formula, if f of x equals x squared, instead of making an xy table, you could make an f of x table. Instead of saying that when I plug in 2, I get y equals 4, I'm going to say when I plug in 2, f of x is 4. Okay, so f of 2 equals 4 means x equals 2, output equals 4. And the output goes on the y-axis. It's the point. When you plug in 2, you get 4. It's the point, 2, 4, just like it always was. It's just that we have this new way of talking about it. F of 2 is equal to 4, like this. Okay, well, some people make an entire lesson out of that, and up until now I've done the same, but I'm thinking maybe we don't really need to. I'm thinking maybe that's a fast enough introduction to the idea of function, because what's going to happen now is we're just going to keep using the notation over and over and over, and we're so going to get used to it. Trust me, we will get used to it. Okay, so switch colors. What we got to do now, we've got to get to that library I was talking about. We're going to build a library, some examples of functions. Here's one. This is an example of what we would call a linear function. Why would we call that a linear function? Well, remember back in the old days when we were saying y equals mx plus b? If we saw an equation that looked like that, we'd say, oh, the slope is a half and the y-intercept is -3, right? We'd say y equals 1/2 x minus 3 means a straight line with a slope of a half and a y-intercept of -3. Well, what's the difference between what I wrote here and what I wrote here? The only difference is that instead of y, we're saying f of x. That's the only difference. We're embracing the new notation. We're just like so going with it. We're saying, yeah, man, f of x. So the graph is going to come out exactly the same. There's the good news. So I can interpret this as the y-intercept of -3. Let's just do that. I can say the slope is 1/2. So you remember how that works. The old up 1. That didn't look spaced very well. Come on, you. Come on, you. The old up 1 over 2, right? Up 1 over 2 to give me a slope of 1/2. Up 1 over 2 again. Gets me another point. Up 1 over 2 again gets me another point. And if I were to plot every single possible solution to that equation, the points would all blur together and give me that nice little line. So the only other thing I'm going to do different is instead of calling that the y-axis, we'll label it as f of x. So here's another way to think of functions. I think of a function as, think of a dial on the x-axis. And you can slide the dial back and forth, or maybe a slider instead of a dial. Think of a slider. You slide the dial back and forth on the x-axis to set your input. So let's say I set my input to 4. If I set my input to 4, I get an output of -1. The input is x equals 4. The output, that's supposed to say input. The output, and you try not to use a y, but I will. I think that's -1, ain't it? Something like that. And so you've got the point, 4 equals -1. But you think in terms of a function is something that you can set your slider back and forth on the x-axis. That's how you set your input. And then whenever you stop the slider at any one particular point, you're going to get one answer for the output. You do it by looking up on the graph. You say, well, there's my output, right? It follows a vertical line test. You're never going to get more than one answer for your y-coordinate for your output. Anyway, linear functions are just linear equations. They are the same as they've always been. mx plus b. They are straight lines with this one thing that instead of using a y, we're using an f of x. Okay, f of x. Okay, that's that one. 4 more to go. Let's look at the absolute value function. So again, in the old days, we would have made a graph of x versus y. But now we're not using y, we're using f of x. Okay, you get used to it. It was weird for me at first too, but you get used to it. The point is, what's the graph look like? That's what I really want to get across in this point. What do you get when you graph the absolute value of x? Well, you can plug in some sample values. A lot of times what I like to do when I'm just starting with a graph is I always use these values. -2, -1, 0, 1, 2. It's amazing how useful they are. They're not always the best values, but they are often the best values. So if I plug in a -2 here, right, the question is, what's the absolute value of -2? Well, the absolute value of -2 is +2. What happens if I plug in a -1 here for x? Well, the absolute value of -1 is +1. The absolute value of 0 is 0. The absolute value of 1 is 1. The absolute value of 2 is 2, and so on. So notice we're always getting positive outputs. So let me just make a few tick marks over here. So when we plugged in x equals 0, we got y equals 0. When we plugged in x equals -2, we got y equals 2. When we plugged in +2, we got 2. When we plugged in -1, we got 1. When we plugged in and you can quickly imagine if we plugged in a 3, we'd get a 3. If we plugged in a -3, we'd get a 3, and so on. You get a perfect V shape. Perfect V shape. And if my graph were to scale, these would be at 45 degrees on both sides, right? They're slopes of 1 is another way to say it. Anyway, they're V shapes. That's what you get. So whenever you have the absolute value of x, it's a V shape. Notice we call this a vertex. So just to get some lingo down, vertex at origin. And it just climbs forever on this side, and it just climbs forever on that side, and it's a beautiful V shape. The domain, the set of all inputs. I can put in whatever I want. X can be anything I want. I can take the absolute value of anything I want, any real number I want. The range, kind of like that parabola we were looking at. Notice we never get any negative values down here. So the range, the outputs, the old y values as we used to call them, are only, well, if I'm trying to stay away from y, notice how difficult it is, from 0 to infinity. So that'd be the domain, that'd be the range, and so on. There's what your absolute value function looks like. Here's a good one. Square root function. We'll be playing around with some square root functions. Now here's an example where if I plug in my usual -2, -1, 0, 1, and 2, I'm going to run into some problems because square root of -2 is unreal, right? You would get an imaginary number. We don't want to deal with graphing imaginary numbers. So I'm just going to say it's unreal. You plug in the square root of -1. Of course, square root of -1 is also unreal. What's the square root of 0? 0. Square root of 1, 1. Square root of 2 is, see, I don't like plugging in 2. Why would you want to plug in 2? Square root of 2. What do you want to do? Get out a calculator and use a decimal? Phooey. Let's not do that. So what I'm going to do is I'm going to change up a little bit. I'm going to plug in numbers that I like. What would I like to plug in here? I'd like to plug in a 4. Do you know why? Because the square root of 4 is 2. See? How about what else would I like to plug in? What else do I feel like taking the square root of? How about a 9? If I take the square root of 9, I'll get a 3. So you want to be a little strategic when you're plugging stuff in here. So when you're doing the absolute value function, these are probably what you want to plug in is 0, 1, 4, 9. If you want to keep going, do a 16 and so on. So what's this graph going to look like? This is x. This is, remember, f of x. And I kind of went out to 9. Let's see if I can do that. 1, 2, 3, 4, 5, 6, 7, 8, 9. There. Well, I didn't go that high, though. Notice I can't plug in negative numbers. I get unreal answers. There's nothing to graph over here. There's nothing to graph over here. I can't use negative x. But when x is 0, I get 0. When x is 1, I get 1. When x is 4, I'm up to 2. And when x is 9, I'm up to 3. I call this a hook shape. It's kind of a hook shape. So square root functions give you nice hook shapes. Notice they have a definite beginning to them. This one starts at the origin, climbs, and it climbs forever, even though it keeps climbing more and more slowly because it kind of hooks over like that. Okay, so it's a hook shape. Ask yourself, what's the domain and range? The domain is the set of all the x values, basically. Look at the x-axis when you're thinking about a domain. So looking at the x-axis, I say, well, there's nothing out here. It starts at x equals 0 and keeps going. And the range does the same thing. Of course, for the range, you're looking at the y-axis. And on the y-axis, we start at 0 and climb to infinity like this. So what you want to kind of keep in mind is maybe a couple things here. First of all, a square root function makes a nice hook shape for you. That's something to keep in mind. And then maybe keep in mind this nice little strategy about when you're plugging stuff in, you don't want to have to get out your calculator and have decimals. Bleh. Just you know, be a little strategic about plugging in. Boy, I'd really like to plug in a 4. I'd really like to plug in a 9. You know, it's a good tip. Reciprocal function. Okay. Well, let's just start with what I was doing before. I'm going to leave some space there, actually. These values are not bad, really. Now, if I plug in a -2, what does that look like? 1 over -2. Well, that's the same thing as -1/2, right? Positive over negative is negative. If I plugged in a -1, you get -1. If you plug in 0, ooh, that's not good. Dividing by 0 is undefined. Boom. Doesn't work. If you plug in 1, well, you get 1. If you plug in 2, well, you get 1/2. Okay. Now, when you start graphing these things, let's start graphing these things. So x goes this way, y goes this way. 1, 2, 3, 4, 1, 2, 3, 4. 1, 2, 3, 4, 1, 2, 3, 4. Okay, cool. So when x is -2, I'm at -1/2, right about there. When x is -1, I'm at -1, right about there. Boom, at 0. I got nothing at 0. I'm going to draw that this way. I'm going to put a dashed line there. That dashed line shows that when x is 0, you do not have any y values. We call that an asymptote, by the way. There is no point anywhere on that dashed line. Why not? Because when you plug in 0, you have a division by 0 error. There is no point anywhere on that. Anyway, let's switch back and keep going. When x is 1, y is 1. And when x is 2, y is 1/2. Now, to get a fuller feel for what the graph looks like, we're going to want to plug in some more values. So let me give you some more values to think about. Let's do -4. If you plug in -4, you're going to end up with -1/4, which is like over here someplace, right? Let's plug in +4, and of course you'll just get +1/4. So that would be x is 4, +1/4. What we've got here is called a horizontal asymptote. Notice if I plug in something bigger and bigger, if I plug in a 10, I get 1/10. If I plug in 100, I get 1 over 100. You get closer and closer to 0, but you never hit it. That's actually called a horizontal asymptote. So we get an asymptote here as well. So asymptote. We got a vertical asymptote all along the y-axis. We got a horizontal asymptote all along the x-axis. This graph never touches the x or y axes. That's interesting. So it's kind of leveling out over here along the x-axis somehow. Just try an arrowhead, try to make it show that it's getting closer and closer. Getting closer and closer. What happens if I get closer to x equals 0 here? Let's plug in a couple more points. If I plug in -1/2 for x, 1 over -1/2, what's that? Well, there's a couple ways you could get at this. One way you could get at this is you could say this is a 1 being divided by a -1/2. A 1 over 1 times the reciprocal. you end up with a negative 2 over 1, which is a negative 2. That's one way to get at it. So this should come out to negative 2. Another way to get at it is, what does division mean anyway? When you divide, you're asking, how many times does this go into this? How many times does a half go into a 1? If you got half a pizza, how many times can you fit it into one pizza box? And the answer is 2. Right? Now it's negative because of that. But that's why you get a negative 2. That's just another way of looking at it. Get rid of the green stuff. Okay. Of course, if you plug in a positive 1/2, you're going to get a positive 2. But let's put those plots in. When x is negative 1/2, I come down to here. When x is positive 1/2, I come over to here. So you can see that, oh, okay, it's going to do one of these deals. It's going to go up along the y-axis. It's going to go down along the y-axis. It's kind of a, I always think of a garden hose. Imagine a garden hose spraying into a corner. So the water goes, whoosh, this way, and the water over here goes whoosh, this way, this way. That's just what I think about. You don't have to think about that if you don't want to. You can, however you want to remember this shape. It's kind of like it splits on the crosshairs. It's like the x and y axes are kind of like crosshairs, right? So you get this behavior where it's kind of going down from the y-axis over to the x-axis, and then over here on the other side, there's the x-axis, and then towards the y-axis. So it does the splits, so to speak. So that's what the reciprocal function does. 1 over x. It does the splits. Okay, let's see now here. I think I got one more function to look at. One more function for our library, and then we'll just start playing with the functions a little bit at the end. So one more function to look at. This one's called the floor function. Interesting symbol, right? Notice the little hooks there. So it's not quite an absolute value symbol. It's got the weird hooks there. So this floor. Now this symbol is actually trying to give you an image. The floor, of course, is on the bottom, right? That's where the floor is. Okay, so how does this work? It works like this. I'm going to plug in a 0. You know what I'm going to get? I'm going to get a 0. I'm going to plug in a 1. You know what I'm going to get? I'm going to get a 1. I'm going to plug in a negative 1. You know what I'm going to get? A negative 1. So far, so good, right? And actually notice it's not an absolute value at all, because the absolute value of negative 1 would have made a positive 1. So this is not at all an absolute value function. This is something completely different. It's a floor function. And all of a sudden, I'm wishing I had kind of made that smaller, but whatever. If you plug in a 2, you get a 2, and so on. So let me just start to graph this. So at the moment, we have like no clue why we would call this a floor function. It just looks like it's like you plug in x, you get out x. That's what it looks like so far. I plugged in negative 1, I got out negative 1. Cool. I plugged in 0, I got out 0. I plugged in 1, I got out 1. I plugged in 2, I got out 2. Okay. This will be true. If I plug in 3, I'll get out 3. If I plug in negative 2, I'll get out negative 2. Okay, so this pattern does continue like that. It's what happens in between that's different. First of all, we are not going to say it's a straight line. It is nothing like a straight line. You might want to think of it as almost like step function. They call it the floor function, but you almost want to think of it as like steps. Here's what it looks like. First I'll show you what it looks like, and then I'll explain why. So this function is going to look like this. Like from here, make a step all the way until, and then you need an open circle here. Why do you need an open circle? Because when you plug in x equals 1, you get 1. And when you plug in x equals 2, you're supposed to jump up to 2. But for anything in between 1 and 2, you're supposed to get out x equals 1. That's worth writing down. For x between, and by between I mean between, not including, but between 1 and 2, the output is 1. It's like you've rounded down, and by rounding down, rounded down. Rounding down means 1.01 rounds to a 1. It means 1.5 rounds to 1. It means 1.99 rounds to a 1. So we're rounding down, 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 down. Okay? And that's why we call it a floor function. It's kind of like you're not on the second floor until you actually reach the second floor. So you don't climb up here to x equals 2 until you actually, or to y equals 2 until you actually reach x equals 2. Until then, stay here along y equals 1. Something like that. I mean, you got to use some kind of words like that to make sense of this to you. But this is the basic idea. It rounds down. So what's going to happen over here? You're going to stay along y equals 2 until you reach x equals 3. And then there's another jump. And this pattern continues forever. And it continues forever in both directions, in fact. And let's try to make sure I put these in the right spots. Something like that. Forever in both directions. It's a bunch of steps. And actually, this is a good thing to keep in mind. It rounds down. It rounds the input down to the lower integer. So if I plug in a 1/2, that gets rounded down to a 0. But notice if I plug in a -1.5, well, if I'm going down to a lower integer, I have to go down to -2. See what I'm saying? Down, and I do mean down. Round down, down. Go down, young man, go down. I don't know where that's coming from. Anyway, it's the round down function. So it looks like a set of steps. If you keep that in mind, you're halfway there. Then you just got to make sure the steps end up in the right spots. So you can remember that, well, you can remember that when you plug in 1, you get 1. When you plug in 2, you get 2. When you plug in 3, you get 3. So that's where I'm getting all of these solid dots. And then your steps go horizontal. And then notice this is actually pretty important. So let's point this out explicitly. Notice this is lined up. So the open circles are lined up with the solid dots. That's actually very important. You don't want to make a step function that looks like this. Okay, that doesn't count because you're missing all kinds of stuff. It's like, what's going on in here? Okay, they should be lined up. There should be no gaps like that. So anyway, you've got a set of steps, and honestly, if you nail down 2 steps, you can just copy the pattern confidently in both directions. It just keeps going forever in both directions. So even though I think the first 2 steps I figured out wasn't it like this one and this one or something? Well, you can just keep the pattern going forever in both directions. That's what it's going to look like. A bunch of steps. Here's a nice question for you. What the heck is the domain? And what the heck is the range? The domain, well, you're looking along the x-axis, and you're saying, what can I plug in? And the answer is I can plug in whatever I want. Right? I can plug in whatever I want, so it's all reals for the domain. The thing is, the range, you don't get out. You know, if you were to look at the y's, if you look at all these y coordinates, you never get fractions. You always get numbers like 0, 1, 2, -1, -2. The outputs are always integers. So I'm going to say all integers would be the easiest way to say that. All integers. You get out things like 0, 1, 2. Things like -1, -2. You get out integers. Okay. Cool. So what are the functions we're looking at? Linear functions, absolute value, which is a v, square root, which is a hook. What else we got? Oh yeah, the reciprocal function, which is kind of like a whatever you want to call that. It does the splits. And these floor function, which is kind of like a set of steps. Now, having those graphs in mind helps you with your Scratch-n-Sniff graphing. Now, later in the course, we're going to learn all kinds of cool ways of taking shortcuts to making graphs. But for now, let's just follow the old, I call it Scratch-n-Sniff. Some people just say make an XY table, but it's the same thing. Make an XY table. Except you don't have to blindly make an XY table because you have an idea what you expect now. You expect when you see x inside of an absolute value like that, you expect some kind of V shape. So just bringing that one little expectation in is going to help you make the graph, because for one thing, you're not going to stop until you find the vertex, the sharp point, the pointy part. You know. So if I started plugging in things like, I might as well just do the same thing. -2, -1, 0, 1, 2. It's never a bad place to start. If I plug in -2, what have I got here? The absolute value of -2 plus 3. What's that? That would be the absolute value of 1. That would be 1. Okay, let's plug in negative 1. So the absolute value of negative 1 plus 3. What's that? Well, negative 1 plus 3 is 2, and the absolute value of that would be 2, right? So that's a 2. If I plug in a 0, what do I get? Well, 0 plus 3 is 3, the absolute value is 3. If I plug in a 1, what do I get? 1 plus 3 is 4, the absolute value is 4, and so on. And so actually, yeah, this is a good one. I like this one. So just to plug in a few values here. When I plugged in negative 2, I got x equals 1. When I plugged in negative 1, I got x equals 2. When I plugged in 0, I got x equals 3. When I plugged in 1, I got x equals 4. And so on. And you can tell that pattern's going to keep going up. But what you're not going to do is say, oh, it's a straight line, because you know better. You know better. It's in an absolute value. You expect some kind of V shape. So we should keep scratching and sniffing, so to speak, going over here. Values, what I mean is over here. Let's see what's happening if I plug in x values over there. How about if I plug in like a negative 3? If I plug in a negative 3, well, negative 3 plus 3 is 0. Ooh. What if I plug in a negative 4? Negative 4 plus 3, right? This is the absolute value of negative 4 plus 3. That would be the absolute value of negative 1. The absolute value of negative 1 is positive 1. So see, we switch directions all of a sudden. When x is negative 3, I'm at 0. But when x is negative 4, I'm at 1. We found the vertex. Woohoo! And so we know it's going to do that, right? We're expecting a V shape. It has to, we're done plugging and chugging. We can just say, yeah, there's our graph. Yay, there's our graph. So that's what I mean by scratch and sniff graphing. It means you're just making up values for x and plugging them in, just make an XY table. But keep in mind what you expect from your library of functions. Ooh, absolute value of x. I expect a V shape. Let me make sure I get where it turns around. Let me make sure I find that vertex, that pointy part, before I stop graphing, before I stop plugging things in. Okay, that was one. Hey, this would be a good one for you to try. Just kind of start your scratch and sniff. Did I use a y up there? I did. I was supposed to use an f of x. I'm not going to care if you use f of x or y. I don't care. But I'm going to try to be good. I'm going to try to use x and f of x. Anyway, try that. I'm going to plug those in first just to see what happens. But you should pause, try to graph it, see what you get. Come back, see what I got. Back? Okay, so when I plug in a negative 2 here, negative 2 plus 3 is 1. Square root of 1 is 1. 1 minus 2 is a negative 1. If I plug in a negative 1 here, I don't want to, because I'll have to take the square root of 2. I don't want to. I won't. Okay, if I plug in a 0 here, I won't. So I don't like the idea of having to take the square root of 3. When I plug in a 1, okay, I'll plug in a 1. I'm happy with that. When I plug in a 1, 1 plus 3 is 4. Radical 4 is 2. 2 minus 2 is 0. Okay, so already, I think I'm changing my mind about what I want to plug in here. What I'd like to plug in, I'd like to have this come out, like if I plug in a 6, then I'll have a 9 here. See, I like that. So I'm going to plug in x equals 6. So 6 plus 3 is 9. Radical 9 is 3. 3 minus 2 is 1. There. I got some points already. What do you say we start graphing? I got to go all the way up to 6. Huh? 1, 2, 3, 4, 5, 6. So when x was negative 2, I was at negative 1. When x was 1, I was at 0. When x was 6, I was at 1. Huh. Okay. Now what am I expecting? I'm expecting a hook shape, remember? So I know that if I keep plugging in bigger values, I'm going to keep going that way. So let me just kind of do this. But remember, the square root function tends to have a definite starting point, right? Let's make sure we find that starting point, which means I should be plugging in some smaller values for x. So let's put some smaller values in. How about if I plug in, let's see, I wouldn't mind taking the square root of 1. So if I make that a negative 2, negative 2 plus 3 is 1. Square root of 1 is 1. 1 minus 2 is negative 1. Here's another point. That's not another point. I already had that point. Okay, let me go further back. I wouldn't mind taking the square root of 0. I wouldn't mind taking the square root of 0. How am I going to get the square root of 0? I'm going to have a negative 3 there. So when I plug in negative 3 plus 3 is 0. Square root of 0 is 0. I get minus 2. So actually, when x is negative 3, y is negative 2. So I found another point. And notice I can't go any less than that, because if I go any less than that, all of a sudden, if I put a negative 4 here, I'm taking the square root of a negative. It's unreal. So that's how you know you found the end, is because you took the square root of 0. I might even write that down as a little tip. Square root of 0 is the beginning of the graph. So how do you get the square root of 0? By plugging in x equals negative 3. And when x is negative 3, I plug it in, I get the square root of 0 minus 2. I end up at this point. That's where it must begin. So right there. So that means that my graph starts there, and there's my hook. That's supposed to be my hook. So that is the full graph right there. And now I get to make a point. PS. If your graph continues in a certain direction, be sure to indicate that by using an arrowhead, like I did over here. Okay, I used an arrowhead over there. Whoops. So those are the points I graphed, right? Is that a good graph? Is that a good answer? No, that's a terrible answer. Why is it a terrible answer? Because there's more to this graph. It doesn't just end there, it keeps going. Notice it does not keep going over here. And so having this solid point and then nothing here is what you want. That's exactly what you want. So you would know not put an arrow on this side, because it does not keep going that way. It doesn't. So when you put an arrowhead, that's important. When you don't put an arrowhead, that's also important. So what a lot of people do, which they need to break this habit, if you're one of these people doing it, break this habit right now. Let's say I asked you to graph a straight line and you did this. Well, that's not done. Straight lines go forever. Put your arrowheads to show that it continues in both directions. Otherwise, there is such a thing as a straight line that starts here and keeps going to the right. There's such a thing. And if that's what you meant, then that's what you should wrote, what you should draw. If it's not what you mean, then that's not what you should draw. Okay, so if the graph continues in a certain direction, be sure to indicate that by using an arrowhead. Okay, I do deduct points for that one. If it continues forever, write it, draw it, indicate it. Okay, so what was good about that example? It was a square root function, so we expected a hook. And the one thing about hooks is not only do we expect it to hook over, but we also expect it to have a distinct little beginning point, a definite point where the graph begins, and then it'll just continue forever in the other direction. So we had to find that beginning point. We found the beginning point. That's part of our mission when we try to sketch a graph like that. 2 examples to go. Now this one, what do you expect? Well, it's hard to expect like what the whole graph is going to look like, but you can expect something about it. The 1 over x part kind of indicates some kind of that, right? We expect it to do the splits. We expect this thing to do the split. Do the splits. Maybe I'll just write it that way. It'll do the split. Come on, you. It'll do the splits like 1 over x does. That's a little more succinct to say it that way. So where is it going to split? You know, I don't know. You do have to do some scratch and sniff at some point. So x, f of x, okay. If I start doing things like plugging in, I don't know. Let's just think about these. If I plugged in a -2, what would I get? 4 minus 1 over -2. Well, that means 4 plus a half. Guess I'll write in 4 and a half. Cool. What happens if I plug in -1? 4 minus 1 over -1. Well, that would be the same as 4 plus 1. That would be a 5. Okay. What if I plugged in a 0? Whoops, plugged in a 0. I'd have 4 minus 1 over 0. Oh, there's my boom. There's one of my booms, right? Because of the division by 0. Boom. Got a real problem there. That would be one of those asymptotes, the vertical asymptote, actually. Well, that's cool. We found one of them. Now let's plug in x equals 1. 4 minus 1 over 1, which would be 4 minus 1, which would be 3. This is goofy. Okay, if I plug in a 2, 4 minus 1/2, that would be 3 1/2. Okay, that's goofy enough for me to stop and graph the points and see what I'm looking at here. Sometimes you have to graph the points to get an idea of what you need to do next. So let's do that. So let's see, I got to go out to at least 5 or 6, it seems. Okay. Points. When x is -2, I'm at 4 1/2. That would be something like here. 1, 2, 3, 4 1/2. Yeah, something like there. There's that point. When x is -1, y is 5. So that was just a little bit higher. Okay, cool. When x is 0, we boomed. I'm going to put the boom in a different color just so it shows up nice. Asymptote. All of a sudden I got Despicable Me in my mind. Asymptote. Knocked over. Anyway. When x is 1, y is 3. That would be right about here. Okay, cool. When x is 2, I'm at 3 1/2. What? Okay. Okay. Now I understand the 3 1/2. I was like, why is it going up? But anyway, here's why it's going up. It's because I'll bet you the horizontal asymptote's somewhere in there, and it's going to go something like this and something like this. See, having that expectation that it's going to do the splits helps quite a bit when you're trying to generate a graph. So, let's get rid of these things. Let's plug in some more points, shall we? Let's plug in, I don't know. You can look at the graph to figure out. What else do I want to know? How about if I plug in something way out here? How about if I plug in like a 4? Now what do I got? I got, well, let's see, 4 minus 1/4. Well, I got 3 3/4. So notice it goes just a little bit higher. And if I plug in, let's get really big. Let's plug in an 8. If I plug in an 8 here, I'll have 4 minus 1/8. Well, see how we're like just going to be 4 minus something small. So now we're at, what did that be? 3 7/8. Okay, I can tell where this is. This is along y equals 4. That would be our asymptote. So try to draw that as a nice dashed line. And notice we got enough information to finish our graph because I know that it's going to go down along that asymptote. It's got to go through the points that I found, and it's got to hug that asymptote. The graph has to look something like that. And then over here, same deal. It has to hug that asymptote. It has to go through the points I found, and it has to climb up along that asymptote. So 1, 2, 3, 4, 5, 6, 7. I only plugged in 7 points. But because I knew a little bit about this 1 over x function, I was able to just do the whole graph, boom. And it's nice, it's accurate, it's a nice sketch. Hopefully you're starting to feel the power of having a few functions in your memory there. Put some functions in your memory, it makes the rest of your college algebra life easier. All right, this is the last example for today. And again, I'm going to invite you to try this. Remember, that's the floor function, not the absolute value function. What do we expect of the floor? We expect steps. Remember these steps? Something like this. Now the steps are getting changed a little bit because there's a 2 in there. That's got to do something. But that's what you kind of expect. Expect steps. I'm just going to go like this. Steps. Okay, see if you can graph that real quick. Or even real slow. See if you can graph that. Back. Okay. First, I will do my usual plugging in of -2, -1, 0, 1, and 2. And if you plug in a -2 here, what have I got? I've got 2 times -2 is -4, which rounds down to -4. If I plug in -1, what happens? I got 2 times -1 is -2, which rounds down to -2. If I plug in a 0, of course, or if I plug in a 0, then of course 2 times 0 is 0, which rounds down to 0. If I plug in a 1, 2 times 1 is 2. That'll round down to 2. If I plug in, come on you, if I plug in a 2, 2 times 2 is 4. I'd have the floor of 4, which means take a 4 and round it down. It rounds down to a 4. Well, what the heck are these points looking like? Let's just see now here. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. So when x was -2, I went down all the way down to 4 here. And that's a solid dot. When x was -1, I go down to -2. I really do. Boink. When x is 0, I was at 0. Huh. When x was 1, I was up at 2 already. When x was 2, I was up at 4 already. Okay, we go through those points. We're expecting steps. Okay, well, question. Do you think I could just do this? What do you think? Could I just do this? Well, I'm a little nervous that we didn't find a -3 in between the -4 and the -2. So I'm going to say maybe, but I'm not going to go that quickly. I don't want to take any chances. What I'm going to do is I'm going to plug in some more values. Like, how about if I plug in something in between? Let's go down here. Something in between 0 and 1. What happens if I plug in a 1/2? If I plug in a 1/2, I've got 2 multiplies a half. Well, 2 times a half is 1. Oops. 2 times a half is 1, and if I round a 1 down, I get a 1. Aha, see? So when x is a half, I get this. Oh boy. And I think I know what's going to happen here. If I plug in 1/2, what's going to happen? Come back up to here. If I plug in 1/2, I have 2 multiplying 1/2, which of course is 3. And if you round a 3 down, you get 3. So when x is 1/2, I'm up here at 3. And that's what's going to happen. So the steps are only half as wide as they used to be, is what's happening here. So the step doesn't go from 0 to 1, it goes from 0 to a half. So this step only goes halfway. Whoa, let's make sure that looks open, because there's going to be another step here. So I'm trying to put a solid dot like this and then like this. It might be easier if I had used a larger scale on that. So just let me zoom in. Let me just graph out to like 2 in all directions, just so we can zoom in and see the pattern better. So when x is 0, we go out to a half like this. That's a step. Jump up. Boy, it's still kind of hard to draw, isn't it? Okay. Okay, just for that. Just for that. Come on. I bet you I could draw a straight line if I did it right. How do you draw a straight line? Isn't there a way? Anyway, pretend that's my xy axes, right? So let's call this x equals 1. Let's call this x equals 2. Let's call this x equals -1. Let's call this x equals -2. Let's call this y equals 1. See, it's hard not to keep saying y. Let's call this y equals -1. Let's call this y equals -2. Okay, so the pattern goes like this. From here, you go out halfway. Then you jump to the next step and go halfway. Then you jump to the next step and go halfway. Come down. Well, I'm going to write all over my -1 here. That's an open circle. Come on down. Like this. Steps are half as wide. That was the net effect of putting that 2 inside of our floor function there. Okay, well anyway, this is the kind of detective work that you got to do when you're scratching and sniffing at these basic functions. But again, having an idea what the floor function looks like aids you tremendously. Look, I'm looking for steps. Let's try to find the steps. Or with this one, look, I'm expecting some kind of a crosshairs or do the splits or whatever you want to call it. So let's find the splits. Here I'm expecting some kind of a hook. It'll start at some point and keep going. Here I'm expecting some kind of a V shape and so on. So these are some functions that we can play with as we get back to our scratch and sniff graphing and have a good time with our library of functions. Whew, I think that was a long one, wasn't it? 55 minutes.